So we've talked a lot about angle relationships and angle and arc measure relationships in circles, but we also want to talk about what do we know about segment lengths. So we want to look at segment relationships in circles, and this time we're focusing on the actual measurements of the segments. So we're looking at, for example, the length of 5 inches or 2 units or something like that. So we're not looking at degrees anymore. We'll be looking at the measurements of the segments. So we basically have three different combinations, because if you think about the different types of segments we have with circles, we have chords, secants, and tangents. We have different combinations of like two chords put together or two tangents put together and things like that that we can work with. So we basically have three theorems we're going to be going over to finish off our segment relationships in circles. And the first one deals with two chords. All right, so this first theorem is called the chord-chord product theorem, and you can see we have two chords and they have to intersect. So we don't always have to have intersecting chords, but when they do intersect, these segments have a relationship. So it says that the products of the lengths of the segments of the chords are equal. So what are the lengths of the segments of the chords? So there's a lot going on there. So for example, if we look at this chord CD, it's made up of two pieces. It's made up of CE and also ED. So the lengths of the chord CD are CE and ED. Okay, so those are kind of like the two parts that make up the whole thing from C to D. So what this theorem is telling us is if we multiply those those parts of the chord, those segments, so for example, if I multiply CE times ED, it's going to equal the product of the parts of the other chord. So it's going to equal AE times EB. So that's what this theorem is saying. All right. What you want to be careful of is we've seen this diagram before when we were looking at angle measures in our circles. So be careful when you look at the directions. Are we looking at the length? Or are we looking for a degree? And that should give you a huge clue about which equation to set up. So if we take a look at example 1, we want to find the length of x, the value of x and the length of each chord. So first we want to see, okay, well, what is intersecting here? Well, these are two chords, right? So the chords are GH and EF, right? So we have two intersecting chords. They intersect inside the circle, but I don't really care about the angle measures. I'm looking for the length. So the length is what tells me, okay, I'm going to use my chord-chord product theorem. So what are we going to multiply to solve for x? Well, using that theorem, we're going to say, okay, the parts of GH are GJ and JH. Multiply them together, and they should equal the product of the parts of EF. And what are the parts of EF? Well, it's going to be EJ and JF. All right, and then just substitute in what we know. So in this case, we have all the different parts, but if we don't, we can always use things like the segment addition postulate, just add or subtract to find the missing value. So just look out for that, right? But this one's nice and easy because we have everything we need to know labeled in our diagram. So 14 times x equals 10 times 7, and then we just solve. So x is 5, so there's part 1 of my answer. And then we want the length of each chord. And be careful, the chords are not necessarily congruent. They're going to be congruent if they happen to be diameters, but or they could happen to be congruent just by chance. But we don't know that for sure, so make sure if you're looking for each chord, we solve for them separately. So GH is 14 plus 5, or 19. And EF is 10 plus 7, or 17. So we want to make sure we answer all parts of that problem. So that's our chord-chord product theorem. Again, you're looking for the word length. That's how we know we're using the product theorem rather than using the angle relationships we talked about before. Okay? So next up, we could have a different combination. If you look at this diagram here to the right, we've got two secants. So we have a secant-secant product theorem. So the secant-secant product theorem states that if two secants intersect in the exterior of a circle, so they do have to intersect outside the circle, because if we had two parallel secants, they'd never intersect, so just something to keep in mind. But anyway, if we see that angle outside the circle and there are two secants, then the product of the lengths of one secant segment and its external segment are equal to the product of the other secant segment and its external segment. So there's a lot of segments going on in there, so let's break it down into what each one of these mean. So when we talk about the length of a secant segment, that's the entire secant. So for example, all the way from A to E is the length of the entire secant segment. That starts from one point on the circle all the way to the point of intersection outside that circle. So this is what we call a secant segment. And then if we're talking about just the external segment, if you think external, that means outside, then we're just looking at the piece outside. So from B to E, that's the corresponding external segment for that secant segment AE. So what we're doing is we're multiplying the entire segment by just the piece outside, and that should equal the product of the other secant segment and its external segment. So it would be AE times BE, so that's the entire secant segment AE times the external piece BE, is going to equal the entire secant segment CE times just the outside piece DE. So that is our secant-secant product theorem. Okay, and again, how do we know we're going to use this theorem? When we're looking for a length. So if you look at example 2, you'll see that in the directions it tells you find the value of x and the length of each secant segment. So when we're looking for length of a segment, you're like, okay, let's do one of those products. Or let's look at that relationship with the lengths. So here we notice it's two secants, it's intersecting outside your circle. So what we want to do is we want to recognize, okay, what are the secant segments? Well, we have GE and we have DE. So then we want to actually work with those entire lengths. So the length from G to E, use your segment addition postulate, what would that be? It'd be x plus 8. The length from D to E, 9 plus 7, 16. And then we want the two external pieces, which are the outside. So that would be the 8 and that would be the 7. And then we can go ahead and put together our equation to solve for x and then each segment, right? So we want the whole thing, x plus 8 times the outside, which is 8, equals the whole thing, 16 times just the outside, which is 7, and distribute and solve. So 8x plus 64 equals 112. Subtract the 64 to get 8x equals 48. So x equals 6. So we're 1/3 of the way there. And then I want to know each secant segment. So I want to know the length of GE, which we said is x plus 8. So that's 6 plus 8 or 14. And DE, which we actually already know from the problem. It's 9 plus 7 or 16. All right, so that's what happens when we have two secants. Then we have one last one, which is a secant and a tangent. And this diagram is not drawn very well. So just imagine this is actually a tangent segment from C to D. So we have a secant tangent product theorem. So this secant tangent product theorem tells us if a secant and a tangent intersect in the exterior of a circle. So once again, these two lines or line segments are going to intersect outside the circle, then the product of the secant segment and its external segment is equal to the tangent segment squared. So you'll notice we have the same situation with the secant segment. So that's actually kind of nice in that it doesn't change. We're looking at the product of the entire secant segment, which in this diagram would go from all the way A to C, right? And then its external segment, which is the same as we talked about before, just the outside, which is B to C. So we're going to multiply AC times BC, and that deals with the secant segment. And then we just look at that tangent segment, CD, and we're going to square it. And that finishes off our equation. So again, if we're looking at lengths, right, you'll notice in the diagram for example 3, we have no degrees at all. Then we can set up an equation using the secant tangent product theorem, right? So we can see that LK is the tangent, LM is a secant, and we can go ahead and put it together. So go ahead and try this out and let's see what we get. So just like before, the entire secant segment is 20, the external piece is 5, so the whole thing times the outside is 100. We're going to square the tangent segment, so 100 equals x squared, square root that. We don't want the negative because x is a length, so it has to be positive, so we get x equals 10. All right, so that wraps up the last of our segment relationships in circles. And if you're wondering, wait, Miss Wong, you didn't talk about a tangent, not in this lesson, but we did earlier. So remember, if we have two tangents, those tangent segments are equal to each other. And that was from earlier in the chapter. Okay, so please let me know if you have any questions. And remember, again, you're looking carefully at the directions, at the diagrams. We use these equations for finding lengths, not degrees, not angle measures, not arc measures. Okay, segment lengths. All right, thanks for listening.